Empirical formula. The word empirical means based on observation or experience. So in the late 1700s, chemists were trying to figure out how elements reacted to form different compounds. And they did things like they'd measure the mass of the first element and the second element, and they'd put them together and it would react, and then they'd measure the mass of the final compound. And then they could figure out the formula of the compound. And so we're going to learn how to do that just from data. We're not actually going to burn stuff or anything. So the empirical formula gives us the simplest whole number ratio of atoms in an element, of atoms in a compound. These calculations are, it's not calculus or anything, but it's just several steps, and the hardest part, I think, is just remembering what to do next. So here are the steps in determining an empirical formula. Find the mass of each element, calculate the moles of each element that are in the compound, find the mole ratio, and to do that, you take each of the number of moles and divide by the smallest one, so the ratios, and then we convert the ratios into whole numbers. So here's our example. A 1.115 gram sample of cobalt was heated with sulfur to produce 2.025 grams of cobalt sulfide. Determine the empirical formula. I'm hoping that that problem is on the next slide. Yes, good. So the first thing we have to do is figure out the mass of each element. There's two elements here, cobalt and sulfur. So what's the mass of cobalt? Well, that's the mass of 1 mole of cobalt. In this problem, in this experiment, what's the mass of cobalt? 1.115 grams of cobalt. Now, it says that that was heated with sulfur to make 2.025 grams of cobalt sulfide. All of this cobalt is still in the cobalt sulfide. But why does this product weigh more? Because sulfur reacted and is in there also. So how could we find the mass of the sulfur in that compound? We're going to subtract. So this is the cobalt and the sulfur. We know the mass of just the cobalt, so we'll subtract. I'll do that up here. 2.025 grams, that's cobalt plus sulfur, minus 1.115 grams just of the cobalt. 2.025 minus 1.115. 0.910 grams. And see here I've got cobalt plus sulfur minus the cobalt. This is just the sulfur. So I've got 0.910 grams of sulfur. Step 1. Step 2, convert these grams to moles. We learned how to do that today. So this is where the 58 thing comes in. We want moles, so we have to divide by grams, and we look at the periodic table. 58.93. 1 mole of cobalt is 58.93 grams of cobalt. 1.115 divided by 58.93 equals 0.01892. In calculating empirical formulas, you really do not want to round off too much. Sometimes students will round that off to 0.02. Significant figures don't tell us to do that. This one has 4. This one has 4. We should keep 4 here, and maybe even a couple of extras. So that's the last sig fig, and I'm going to go 0.08, just for good measure. That's moles of cobalt. Converting sulfur grams to moles follows the same pattern, but the number's different. We look at the periodic table, and 1 mole of sulfur is 32.07 grams. So we've got 0.91 grams divided by 32.07, and we get 0.02837, 1, 2, 3, 4, 5, 4 moles of sulfur. So we could write the formula of this compound as CO 0.0189208, S 0.0283754. That would be tedious, wouldn't it? In a compound, there could be, 2 cobalt atoms to 1 sulfur atom, or 1 cobalt to 3 sulfurs. There's a small whole number ratio of atoms. There's a small whole number ratio of moles, too. And so to get these ugly numbers to be nicer numbers, we're going to look at these and say, which is smaller, 0.02 or 0.01? 0.01. So I'm going to divide both of them by the same number. Well, that one's easy, right? That one comes out to be 1 exactly. I'm going to divide this one by the same number. I have to do the same thing to both of them so that I maintain the same ratio. So 0.0283754 divided by 0.0189208 equals, this equals 1.49969. What's that really close to? 1.5. So this is telling me that the ratio of cobalt to sulfur is 1 cobalt to 1.5 sulfurs. Those aren't whole numbers, are they? If I multiply them both by 2, would the ratio still be the same? So if I multiply this by 2, what do I get? Yeah, I get 2.99939. Is that really, really close to 3? It's really close to 3. We can call that 3. If I multiply 1 times 2, I get 2. So those are my subscripts. It's cobalt 2, sulfur 3. That is the empirical formula. The smallest whole number ratio. When you're looking at these numbers, if you can round it to a whole number, just flat out round it, it's going to be very close to a whole number, like the 2.999. Yes?
Why doesn't cobalt have the number?
Because then you would be able to figure out the formula from the name. Yeah. Because the proper name for cobalt sulfide would have a Roman numeral specifying the charge. So here you could make up a backstory and say, well, they had this, cobalt and sulfur, but they didn't know which cobalt sulfide was formed. Good question. So, but a number like 1.49, you can't just round that. You can't round 3.75 to 4. You have to multiply them, bless you. So you can either recognize decimal equivalents of fractions or you can do a trial and error method. I think there's a slide. Skip that one. No? Okay, maybe it's not. This is about 0.5. 0.5 is equal to 1/2. So if you recognize decimal equivalents of fractions, you can figure out what number to multiply. But the trial and error method works too. Try 2. Do you get nice numbers? No? Okay, try 3. Try 4. Try 5. Usually don't go past 5. Let's look at another one. This one is a similar question, so I'm running out of time. I'm not going to work the whole thing out, but I'm going to talk to you about it. So here it says iron can react with chlorine gas to give 2 different compounds. Those are the 2 different compounds. In this experiment, 0.558 grams of iron reacted with chlorine gas and gave 1.621 grams of the compound. Again, the Roman numeral's missing because we don't know which one it is. Which iron compound was produced? So this is very similar to the previous problem. You're given the mass of one element and the mass of the compound. You can figure out the mass of chlorine using subtraction. Then you have a mass of iron, a mass of chlorine. You convert those to moles of iron and moles of chlorine. You look at those numbers of moles and you identify which one is smaller. And you divide both of them by the smaller one. And you should come up with a ratio of 1 to 2 or 1 to 3, and then you know which one is the answer. So you can try to work that one on your own. Let's look at this one. Sometimes they give you percent composition instead of masses. And so this just is another, I guess you could say it's a trick or a hack. So like they say, 92.2% carbon, 7.83% hydrogen. Well, if you say, let's say that we have 100 grams, what would the mass of carbon be? If you choose a sample size of 100 grams, then the masses are equal to the percentages, because 92.2% of 100 grams is 92.2 grams. So let's just kind of start this one. Calculate the empirical formula for the caffeine. I think this is to be for caffeine, given the following percent composition. So we're not given any masses. 49.5% carbon. We're going to choose 100 grams. I don't know where that came from. Just choose 100 grams. What's 49.5% of 100 grams? 49.5 grams. There's a mass of carbon. We do the same thing with the other percents. So we get 5.15 grams of hydrogen. 28.9, that's an 8, grams of nitrogen. That's in the way. 16.5 grams of oxygen. The rest of it's the same. Convert each of those to moles. Divide all of them by the smallest. If you get whole numbers, jump up and down, do a happy dance. If you don't get whole numbers, try multiplying everything by 2, everything by 3, until they'll all come out whole numbers.